All right. Hi, everyone. Happy Thursday. I'm Nat, and today we are going to be diving in deep to the nervous system, understanding the very, very early days of human development, and understanding what does it mean when we say neurodevelopmental condition. Because we throw that word around all the time, neurodevelopmental. What does it mean? Well, neuro, brain, developmental, it's kind of the building blocks. And it is somewhere in this part of early development where conditions such as dyslexia, dyspraxia, autism, ADHD, we believe originate from. So today we're going to be looking at where this might happen. Because again, with most people, you are born being neurodivergent and you are neurodivergent your entire life. And it's understanding like at what point does the brain diverge and decides, hey, you're going to think this way from now on, or you're going to have this perspective. It happens so early on, and we are going to be kind of trying to pick that apart, just so we all know, in terms of the difference between neurodivergent and neurotypical brains, it's hard to say, but we can definitely say at what point this is likely to occur. Like visibly much difference, more research is still needed. Okay, so today we as an organization, we specialize in dyslexia, dyspraxia, autism, ADHD. And these are ways that the brain process information. But where does neurodivergence come from? Well, some say it's nature, some people say it's nurture, other people, it's genetic, other times it's external factors. Most people will agree it's genetic, meaning it's like baked into your DNA. But we are going to be looking at those ingredients which creates the baking and kind of looking at that. It's quite complex, but I'm going to break it down as simple as possible. So really do let me know if you want me to go into more detail, less detail, break it down, and I'll do my best. Now, as an organization, we are a support agency that supports people into employment. So anyone who resonates with being neurodiverse can get support. And here's a picture of me, just so you know what's my background. 1, I'm neurodivergent, so expert via experience. 2, I support people every single day who are neurodiverse. And 3, I'm currently doing my master's in neuroscience. And this is where I'm going to be drawing a lot of my experience from today. So while this has been heavily researched, if anything is out of date or you want to challenge me on, I'm very welcome to that as well. Now, we deliver these webinars every single week. And the last one we did, which was on psychosis and antipsychotics, which is really interesting. We often talk about neurodivergence, but not so much mental health. But some people may argue that psychosis is a form of neurodivergence. The argument for it is, well, does it mean you think and process information in a different way? Yes. Well, maybe that's neurodiverse. Other people might say, well, it's something you can develop and it's debilitating and it's more negative than positive. So it's more mental health. It's an interesting debate, though. But either way, a lot of people who are neurodiverse also have co-occurring mental health challenges, hence why it's included regardless of how we label it. So do check that out on our YouTube channel. All right, so let's get to it. Building a neurodivergent brain. It's not as simple as just thinking, hello, this is the neurodivergent part. We don't really know what genes create neurodivergence. We don't know at what point it kind of is a thing, but likely it's a combination. It's probably not the same for every single person. So I'm going to start off quite an open question. What is meant by neurodevelopmental disorder? Like, to your understanding, when people say, oh, I've got a neurodevelopmental disorder, or, yeah, no, that's neurodevelopmental, what do you think is meant by it? At kind of what stage, at what part? What is the key difference between having a neurodevelopmental disorder and a mental health disorder? Are they the same thing? Are they different? And just have a go. On the app, it's completely confidential. So I just want to kind of understand how you would define it. Okay, let's have a little look. We got the brain doesn't develop in the same way that it does in most. Yes, that's a good way of putting it as well. Because we use the word disorder, right? Let's be fair. Disorder is real negative, and it's much better to not use it. However, in a clinical perspective, disorder means just out of the ordinary, dis as in not, and order as in conventional. So something which is neurodevelopmental disorder is just, as you said, a different way of developing information. We've got, these include dyslexia, dyspraxia, autism, and ADHD. Yep, they do. The way they process the world is different from birth. Yes, that is a really good one. You can have things called acquired neurodiversity. So you can get acquired dyslexia and acquired dyspraxia. This is, say, if you've had like a car accident and you've had severe trauma. So it is possible, but they are different things. It's just the way that it presents itself and the characteristics overlap dramatically with neurodevelopmental ones. Brain structure differences, nice. Brain works differently to what is seen as normal. I like that what is seen as normal. Normal is perceptive. Development of the brain is outside of typical standards. Brain is programmed differently to other people. Apple v Microsoft, nice. I feel like someone's been to my previous sessions. Mental health may be more influenced by external factors and neurodevelopmental disorders. Oh, yes, that is also an interesting point. Okay, so now we're on the same thing. We are going to be breaking that apart. Neurodevelopmental is just changes in the brain very, very early on, literally from like day dot of the egg kind of being fertilized. And that is what we're going to be breaking down on. So to start off with, we must look at the CNS, and this is the central nervous system. Sounds kind of fancy. It's just the kind of old part of the brain plus the spinal cord. Those two things together create the nervous system. And this is like the hub. This is where all the fun stuff happens. Part of the nervous system consists primarily of the brain and spinal cord. So when I say about the nervous system, we're talking about these two things. And today we are going to start far away and we're going to zoom in more and more and more and more until we're on like the mini cellular level. So quick question, in terms of developmental levels, is there an area you feel most comfortable with? First of all is systems level. So this is understanding in development, you know, the changes, the shape, how things affect you. The second one is diving a little bit deep, well, a lot deeper into cellular level, like looking at neurons. And the last one is, I have no idea. I don't know any of this. Either's fine. Okay, cool. We are going to be starting off from the systems level first, and then we're going to be zooming in slowly. And again, at what point does neurodivergent develop is up for debate, but it's still useful to kind of see at what point can things go different or wrong. Now, in terms of what one you think is right, you decide me, because sometimes, you know, the brain doesn't develop conventionally. Now, it's a fine line between when something is just alternative and when other things aren't working correctly. Interesting debate. So starting off with the systems level, and essentially the systems level just means how different parts of the body work together. So how does the brain work with the spinal cord? How does everything fit together like a big old jigsaw puzzle? And we're going to give you a bit of a kind of overview of the first couple of days of being human. I'll try and break this down as simple as possible, but it's very useful to know this in order to understand at what point in the development is neurodivergence likely to occur. So this image here is quite a good one. It just shows you, okay, first of all, we've got fertilization. Then you've got something called a zygote, not related to goats at all. Then we got the cell stages where things start dividing. Then you kind of get blocks of cells, then more cells. Before later, you've got a big old lump of them. Then eventually it develops into a blastocyte. Now, I'm not expecting any of you to ever heard of these terms before, so I'm going to take a little bit of time and break it down a little bit further. So first of all, fertilization occurs when sperm cells penetrate the egg cell. So sperm, egg, penetrate, that is a start. Most people are familiar with that part of the life cycle, but then it's what happens after that where it becomes a little bit grey. First of all, a fertilized egg is now called a zygote. Okay, zygote. Nice. We've got that. We know what a zygote is now. It's just a fertilized egg. Then on day 2 to 3, give or take, the zygote, remember the fertilized cell, begins to divide into multiple cells as it travels through the fallopian tube towards the uterus. I kind of imagine this like going down a water slide and doubling. So like, oh, got a twin now, got a triplet, got a quadruplet, octuplet, just like boop, 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 and dividing lots. And this division is really rapid. Again, we're only on like day 2, and already there's now lots of the same. These cells are kind of neutral at this point. They don't, they could be anything they want in the world. The world is their oyster. Now, on day 4 to 5, the zygote continues to divide and forms a hollow ball of cells called a blastocyst. So you see on this image here, once you've got this nice bouncy ball of cells, the middle bit starts to hollow out and you kind of like creates different layers. So what was like a big, massive lump now is more like a ball that has kind of air inside. Now we're on day 6 to 7. And the blastocyst, this is again the ball which is a bit more like hollowed out, reaches the uterus and begins to implant into the lining of the uterus. So you've got these cells that divided, then you've got a big ball that have hollowed out, and it gets to the uterus and then it kind of absorbs into it. And this, I'm going to be breaking this apart a bit more so we kind of really understand this process, because it is at these points, every time something divides is potential for something to go amiss. When it comes to cloning, you only need like one thing. Like, let's say there's an error, you're duplicating the error, then duplicating the error again. And before long, you've got loads of errors. So let's go back a little bit to day 3. Day 3 after fertilization, embryos have 7 cells. So you see here, 1 cell, 1, 2 cells, 1, 2, 3, 4. So 7 cells. 5th day, the egg is a blastocyst. So you can see how rapidly these have all divided and grown and expanded. It's really fast. And that is when it starts to hollow itself out. And the hollowingness is really interesting. So I think every time it like duplicates, let's say the first cell, it was, slightly different, a little bit unconventional, going against the grain. Well, that's going to be replicating that again and again and again and again and again. So maybe depending on what point, like something is different, might depend on how much things affect you in later life. Just one hypothesis. There's many kind of different ways of kind of doing it. Again, Pete, this is still a developing area. Now, let's see if we're all listening and all paying attention. Which of these images would you say is a blastocyst? What a cool name, though, isn't it? Blastocyst. I feel like that could be used for something else. So nice. Okay, we've got, oh, yes. Well done, everyone. Blastocyst. And you can see the middle there is starting to be hollowed out. So that is a blastocyst. This one is a zygote, and that's just a fertilization. Okay. It's good to know we're on the same page. So now we're looking at this blastocyst. The rearrangement of cells into the blastula into 2 layers. The lining cell, the inner cell mass, and the tropoblast, formalization. Let's not get bogged down on too many details, but the most important thing is there's 2 layers. We are starting to build a cell hamburger, multiple layers. And these layers are also going to be very interesting and useful. So here's a bit of a breakdown of those layers. Again, think of it a bit like a hamburger. So you've got an internal layer, a middle layer, an external layer, and all of these different layers are brimming with potential. They can be so many things. You can be the internal layer, might be a lung cell, digestion cell, skeletal muscle, tubular, red blood cell. We've got skin cells, neuron brains, pigment cells. So essentially, everything which makes a human being is already in this cell. And that's amazing, isn't it? Like, all of you was in this one thing. And when all of these cells start to rearrange themselves into a layer, so again, we've gone from like a hollowed out ball, and now it's kind of rearranging into like a burger, like flat layers. And this then changes name yet again into a gastrulation. So the names change a lot. But again, it's at any of these stages where potentially your neurodivergence is born. So while we say it is from birth, at what point does neurodivergence kind of like spark off? Could be at any of these stages. And as I said about how the layers, so now we've kind of got this burger, and now this burger like starts sinking and like a tunnel appears. And this is called neuralization. So neuralization is a process in which the neural plate, remember this kind of like burger layer, bends up and later fuses to form the hollow tube that will turn into the brain. I'm trying to think of like a bit of paper that just kind of folds in on itself and then it creates a tunnel. I like to think of it like a train. And this kind of like tube, now this is potentially going to be the brain and the spinal cord. So you can see how slowly things are developing, things are growing, and we're now in the very beginning stages of building our brain. So we're building our brain. We've made a tube. It's not a bad start to a brain. And this shows you in a bit more detail how the brain develops. So this is a baby brain, and you can see that the tube is starting to develop. The neural tube forms the early brain and the spine. So at the moment, our brains and spines are still a bit gooey, still a bit malleable, but it all started from original cells, then a zygote, then a blastocyte. It's kind of growing and growing and growing. I remember we're still in only like the first week. It's amazing how like quick it develops. Now, this thing that looks like an alien, believe it or not, is actually human. I know you're like, oh, did I really look like that in my baby photos? Remember, we still have a tailbone, so it kind of looks really freaky looking. Morphogenesis is a process that causes a cell to develop into its shape. So at first of all, I think we look like a bit of a shrimp. Some people say we look like a bit of like a comma. And this is our starting stages. You can kind of see you got the back there, you got the head, you've got the eyes. And what's really interesting is that if you look at the animal kingdom, we kind of all look the same at this age. It's quite difficult to tell the difference. It's only a bit later down the line do we become obviously human. And so with that, I want you to look at all these three images and tell me which one you think is a human embryo. And if you're like, they look exactly the same, it's a really good point on how we all look quite similar. Okay, Georgia says second. Okay, oh, we got a very mixed. It honestly is difficult, but it proves point that in the early stages of existence, we aren't that different from our neighbors. It is actually the first one. Obvious, right? You can clearly see the little fella's eyes and mouth, but they look the same. So still really interesting. Though we are developing rapidly, we aren't exactly what you'd call human yet. We could be anything at this stage. And this is another way of demonstrating it. So here in the first weeks, this is how like a lot of animals look. You got your brain, you got your midbrain, and it's a bit of like a long line. And kind of think of a brain as being like a balloon. Have you ever got those like long balloons? And when you go, like you get this puffy bit at the end, and then it gets bigger and bigger until eventually you get that circle. So the brain eventually kind of like puffs out, and the cerebellum gets bigger and bigger. And then you got your spinal cord. At birth, now we've got a brain. Yay, we've got a brain. And somewhere, this brain is already neurodivergent. We know that by the time it's fully developed, you're already autistic if you are autistic, and it's somewhere in the previous stages that we talked about where it happens. So this is just a quick check-in to find out how are we all understanding. Understand it well, we're not completely sure, or do not understand it in the slightest. All right, I will say this is good. It means, well, if you're not understanding it completely, do not be like worried. It's a complex subject. So the fact that you're even here right now is really great. And it's great to those ones that are. So now that we've got a good idea on the systems level, how everything plays together, let's go even deeper. Because to be honest, we've looked at things from like a mini micro level. We still haven't found the OG neurodivergence. We still haven't really seen at what point do we clearly become ADHD or autistic. So I think we need to explore a little bit deeper. So we're going much deeper now. And if we remember our good friend, the blastocyte, this kind of ball of cells that's hollowed out in the middle, if we zoom in even further, you'll see that we have stem cells. Now, you might have heard of stem cells in the media. They're essentially like baby cells, which could be anything they want to be in life. Again, they have endless possibilities. These are the real fabric of everything. So I don't know, maybe at this stage I could be anything. And people think, oh, maybe I want to develop different organs or cure for things. Well, using stem cells is a good place to start because these cells haven't decided what they want to be yet. Imagine all these stem cells are all in school and they're all being say, hey, what do you want to be when you grow up? Who knows? Some of them might decide to be neurons. Others might decide to be blood cells. Others could become liver cells. And a neuron is in the brain. Blood cells is running through your body. These are very different things, but they all originated from the very same place. Now, liver cells and blood cells isn't what creates neurodivergence. Now, neuron cells, the cells in the brain, now this is a really good place to dive in a little bit deeper. Now, which of these images is a neuron? Remember, a neuron is the kind of talky part of the brain. Neurons allow communication and information to process in the nervous system through electrical and chemical signals. They're essentially for thinking, feeling, and movement. Yes, all of you got that right, which is great. It's just to connect like the cables that are connecting. And you have one end that takes the information in, and then the other end that sends the information out again. Now we know what a neuron cell is, and that is probably going to be the main cell we're going to be focusing on. The part which the stem cell turns into the neuron cell and the nervous system is called cellular differentiation. It's kind of like when a caterpillar turns into a butterfly, how at one thing you're a one thing and then you transform into something completely different. And again, at this stage, you become a muscle cell, fat cell, bone cell. So there's not really anything that can go that wrong at this stage because it's just too early. We spoke about, well, is it when the cell is dividing when maybe you become dyspraxic? Well, unlikely, because at this stage, you could still be a fat cell. Is there such thing as an autistic fat cell? No. So we pretty much know the system level, it isn't looking likely. But the cellular level, now this is when we start to divide a bit and become a bit more specialized. So it's definitely a good contender. But the real next question is, well, okay, Nat, you said that these stem cells can become anything in the body, but do they get to choose what they want to do? Or is it kind of out of their control? How is it distributed? Well, the way that this has been kind of explained is through Waddington, and he saw cells as pebbles rolling down a mountain. Sounds very therapeutic, with hills and valleys. The bottom of the valleys represent cells of differential states. So I kind of also think like a marble run. Imagine you've got a hill and you've got like lots of marbles and you let the marbles go down the hole. Now, some's going to hit a rock and some's going to go left. Others going to go and hit the rock and go right. Or another way of looking at it, when you go to like the arcade or the casino and you put your pennies in that machine and boop, 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 and it could end up in any direction. Here's another way of looking at it. You've got your ball here, and this reminds me more of that like penny machine. It goes down there, boop, in the second level. Okay, we've got 3 different things now. It goes down to the next level and then the next level. And it's done in a way that most things balance out and kind of get into the right matter. Could this be the stage where what makes us is developed? I'm not sure, but I still think it happens maybe a little bit later. And it is this stage when we make all the decisions. So when we've got the cell, the stem cell that's kind of going down this kind of like hilltop, think of it like every time it hits a rock, it's swapping a switch, like. So this is quite a good image because you can see as it going down this mountain, okay, we're going to have that for DNA, you're going to turn that on, turn that off. And if you know anything about DNA, you'll sometimes talk about people turning switches on. Like, okay, well, you have this in your DNA, but this is currently turned off, this is turned on, and it kind of can be seen like this. So when we're creating this neuron, we need to decide exactly what is this neuron actually going to do. And you can see this little spinny wheel. It seems a little bit like a gamble. Woo! Gene expression. Okay, now we're going to decide at what switch is about gene expression, which one is about the axon, which is where the information is taken. All right, we've had that one. So the developmental steps that lead to differentiation. So remember, this is when the cell is not choosing, when is made to be whatever it is going to be in life. And you can have like immature neurons, mature ones, and you can see how they develop over time. So first of all, we have something called neurogenesis, which is the cell division into new neurons. This is what we've been discussing just now. So hopefully we're all up together with that. Then we've got something called cell migration. So brilliant, we've now got a neuron, finally. But the neuron's not at home yet. It's just been born. It's at the hospital. The neuron has to make its way to the house. Now, this is a stage where a lot of people will believe that disorders, difference, neurodivergence, whatever, might be at the root cause. It's when the neuron is going from the hospital into its like forever home. This is where it might get lost. It might get confused. It might not make it all the way back. Then we've got Axonogenesis, neurons development. Sorry about the writing, it's a bit skew-whiffed. This is when we're developing like the little ends of the chemical so they can actually talk to other neurons. So it's these little end bits here that do all the talking. Synaptogenesis. This is when the one neuron meets the other neuron and suddenly they can talk to each other. So like a baby, it's when a baby finally learns to talk and is able to talk to another baby. And lastly, cell death and pruning. This sounds like it's a bad thing. Like, I don't want to have my cells die. It's a natural thing. Think of cell pruning, like going to the hairdresser. It's like, yep, don't need this. Let's trim this up. And it's about making things more efficient. So you see this like line here. Well, this is just a drain on resources. Let's get rid of that and we can put more of our energy. If any of you do gardening, you'll know that you often have to cut branches down in order for other parts of the tree to grow back stronger the next year. Very similar concept. So zooming out again, we've got the fetal brain, the baby brain. We've seen how it develops into this tube. We've seen how the tube kind of forms the brain. And right there, if we get really, really microscopic, we've got the neuron cells, which at this stage can form into glial cells. Now, I don't know if any of you have ever heard of a glial cell. Essentially, in our brain, everyone's always talking about neurons. Neurons this, neurons that. But for neurons to kind of exist, they need scaffolding. They need kind of something to hold them all together. And this is where glial cells come in. They are the building blocks. They kind of keep everything together. So really essential. There is way more glial cells in the brain than neuron cells because they have to hold everything together. And radial glial cells are just ones that are in the brain. So you can kind of see the image here. They're like the kind of little, they're holding everything together. And the next part is, I talked a little bit about neuromigration. And this is, remember I used the analogy of the baby at the hospital going home. So the brain has developed the neurons. It's also developed the glial cells, the scaffolding. But at the moment, the brain cell isn't in the right location. So this is a real image. And you can see here, the neuron is moving along. It's on a bit of a journey. And this is where things can go wrong. They can not make it to the right location. I guess they could get lost. They could die on the way. They might be strong enough. So really interesting part. This is also kind of like putting a puzzle together. So you've got missing pieces in your body as it develops. And it's like, all right, I need more neurons here ASAP. So the body will send the neurons that way so that it can kind of build up its web and map. Now, sometimes this will go nice and smooth. Other times, if the brain doesn't grow as strong connections, this is often where neurodivergent characteristics originate from. It's a brain just not developing particularly as planned in the migration phase. I remember an axon is just a part of a neuron. So neuron is the brain cell, and at the end of the neuron is axons. The axons are just like the ends that hold hands. Yes, nice. You all got it right. So nice and simple. You can see here, as they start to grow, they get more interweaving, and all these little lines are just lots of communications. One cell talking to the next cell, talking to the next cell. And you might think that the more we have, the better we are at communicating. And remember, communication is one of the key challenges with neurodivergence. Not necessarily, because a way you could look at this is, imagine you had like six arms. Sounds better than two, right? But these arms are really weak and scrawny. It's much better to have only two arms that are really strong and muscly than having six arms that are weak and flimsy. And this is the same when it comes to neurons. It's much better to have a stronger connection than having just an abundance of cells. And this is exactly why cell pruning and cell death happens. When someone comes with a chainsaw and starts cutting down the neurons to make it the strongest it can possibly be. Again, this is the area where a lot of people would believe that neurodivergence originates from. Here is another image where you can see at birth, we've got a couple of connections, 1 month, a few more, then 3 months, then 15, then 24. And then eventually, after we get more and more and more, that's when we're going to be cutting back, pruning, finding out. So when people talk about, oh, my brain is just wired differently, it's a really common phrase which is used for people who are neurodiverse. This is kind of what they mean. When we say wired differently, when one neuron connects to another neuron, sometimes it's a straight A to B. Other times it'll be quite a convoluted route, or it might be more interweaving. Sometimes the brain will have more connections, sometimes less connections, but stronger connections. And it's these connections is what we normally refer to when we say the brain is wired differently. And this is called Axonogenesis. Again, really epic name. And this is just the development of the axons. And an axon is the end bit of a neuron that talks to the next neuron. So really important. Without these axons, the neuron isn't really doing much. And as you can see, remember I said how one neuron has to talk to the next neuron. This is a real microscopic view of that. So we've got one axon here. And as you can see, it's growing, it's growing. And as soon as it gets to this end here, it forms this like little ball. But what is really interesting is that our cells, they're not actually connected. They're not joined. There's actually a really tiny gap between. And what happens is they send chemicals and electricity that kind of goes over this little gap. So as you see here, this one here is a completely formed synapse. And there's a tiny little gap. And that is perfectly normal. In fact, is needed. So system genesis is when neurons make connections with other neurons. But while we say connections, they're not actually joined up. There still is this kind of small gap. Here is another example. You can see at birth, you've got a few here. Actually, no, this is a great image, which really explains about pruning. So at birth, we're forming connections. At 6 years old, we've got loads of connections. You know, we're the smartest 6-year-old in the universe. But then at 14, it looks like we got hit on the head a few times. Suddenly, we're losing a lot of our connections. That might seem like a bad thing, but it's not, because these connections are going to be stronger and they're just going to be more accurate. And people who are neurodiverse, for instance, they might prune more of these, or they might prune less of them. So it really depends what the body is choosing to do. This is why when we talk about a spectrum, it's so diverse, because every brain prunes, kills, develops, grows in a different way. So just to summarize what I spoke about today, because it's been a lot of information, is neurogenesis is the birth of neurons. This is where our brain cells come into being. Before this point in time, they could be anything. Then we've got neuromigration. This is moving days. This is when the neurons pack up all their stuff and they're like, I'm going to my main location. At this stage, all sorts can happen. They can get lost, they can die, they cannot make it, who knows? Not all neurons make it. I feel like it's watching one of those David Attenborough shows when you see like little ducks and like, not every duck will make this journey. And you see little dying penguins. That's how I kind of visualize it. Then we've got Axonogenesis, and this is when all the connections start to hold hands. And this can be really good. Some connections are going to be really strong. Other connections are going to be weak. And that is another point which can determine how your brain processes information. So already we've got multiple phases where the brain can choose to do something conventionally or unconventionally or wrong, depending on how it affects people. And then the last one is pruning day. This is when we're like, all right, let's do a bit of a spring clean. Let's get rid of the not very effective connections. And in many ways, I think this quite heavily relates to autism, because autism, it's about how the brain processes information. Sometimes then, like, let's say someone tells a joke and someone with autism might struggle to pull that joke apart because their brain isn't going the most convenient route. They'll go the long way around. And that's because the brain isn't always having the most effective paths in order to get to like the same result. So you can see how, while I can't give any of you a definitive answer about where neurodivergence comes from, we can see at what stages it's likely to occur. Will we know what stage? Maybe one day, but at the moment, probably not. Now, if any of you are neurodiverse and do resonate with being neurodiverse, there is support in the workplace. I can't go back in time to when you were a little embryo and like do some magic, but we can support you now. And this is open to anyone in the UK. But as we got an international audience, I won't focus on this, but get in touch if you are in the workplace. Now, our next webinar, so if you enjoyed today and you want to learn more, we're going to be zooming further out this time, getting away from the cellular level and just looking at a bit of brain autonomy, like understanding what part of the brain does what and understanding that. Because again, really interesting in neurodivergence. At this stage in the webinar, the brain is already made, it's already developed, it's good to go, but it's figuring out what part of the brain does what task and how does it do it? Does it do it well? Does it not do it well? Where's the deficits? And if you also enjoyed, as I said, we do record all these webinars and you are welcome to check out all our previous webinars. Just go on our YouTube channel and type Exceptional Individuals and you can subscribe and you can watch our previous webinars. Have they got any connections between? What do you mean? Like, bipolar and dyslexia. Yes, they do have connections. They are very commonly co-occurring. So if you have one, the likelihood of having another goes up significantly. You're not guaranteed to have one and the other, but you are more likely. So good question. And here is some quick thing on how to contact me. My name's Nat, N-A-T, so just Nat Exceptional Individuals if you want to get in contact, or if you want further support or to learn more about us, just go to exceptionalindividuals.com. You can also message and tweet us. I don't think we've had a tweet in several years, so feel free to message us. And I hope it was pitched at the right level for all of you. And thank you so much for all attending. I'm going to go now, everyone, but have a great rest of your Thursdays and hopefully see you again next week.